All right, thanks for the introduction. And hello, everyone. My name is Huaishu, and this is Jimmy. And today, together, we would like to introduce you RoMA, Robotic Modeling Assistant, a system that allows people to design 3D digital model in the real physical space with an augmented reality headset. And the robotic arm will going to print your design in the same place and at the same time. Now, for many of you who have experience in 3D printing and 3D design, you know this is a quite like time-consuming process, right? You design everything on a 2D screen using a CAD modelers. You generate 3D digital models and for 3D printing, and it always takes several hours, sometimes even overnight, for the designer to finally get the very first version of this physical model. So this separation of design and fabrication process is quite problematic because the designer, it's very difficult for them to get this early tangible feedback during their design process. And also because of that, the designer have to think very carefully when they design 3D digital model, because even a small mistake in their design process can make a significant delay in their design workflow. So in our HCI community, we have this concept called interactive fabrication that is coined by Carl Willis and his colleagues in around either 2011. And basically the concept is trying to retighten this design and fabrication together and consider them as one process. And our RoMA project today is our latest effort that's trying to achieve this interactive fabrication and trying to achieve in-situ interactive fabrication experience so that people can design and printing in the same place and at the same time. Let me start with a working example here. So here, we're going to allow the designer to design a teapot model all from scratch using our RoMA system. On the left side is a set camera view, and on the right side is the first-person view, and let's see how the designer is going to use a RoMA system to design a 3D digital model. All right? All right, so we have this CAD modeling tools on the AR system. The designer is designing this teapot body. You can see the designer can actually put the hand into the design scene and use that as a reference to design the teapot body. At the moment of finish the design, the robotic arm jump in right away, trying to print the user's design in the same place. You can see the right part, we have this yellow rendering lines from the AR scene that maps quite well to this, oh, it works, cool, to this 3D print. And while the robot is printing to the back of the platform, the user doesn't need to wait, but can actually design the next component at the same time. And here the designer is designing this spot, and the designer can actually use this control point to fine-tuning the shape. If the designer would like to design something to the back of the platform, you can simply touch this platform, and you can see the robot is retreat automatically. The designer can rotate this platform, and to repose this model, all the digital and physical rendering is synced together. And the robotic arm can just jump in automatically and to recalculate the printing path and to just printing the new part to the back of the platform. Again, at the same time, the designer doesn't need to wait, but can actually design a new part to the front end of the platform as well. Now the designer is trying to match the cross section to his finger, and he's actually going to put his finger against his just printed part as the physical reference to design the next the handle. And the designer can, of course, fine-tune the shape with all these control points, and once confirmed, that is done for the 3D printing. The designer can observe the printing for a moment, and the robot arm can just automatically to print the new part from the sideway. Now it's printing this spot. And finish the design, the designer doesn't need to be there from all the time, but just satisfied, then the designer can leave. And the robotic arm can take the full control of this printing and also the printing platform. Once I finish this part, as you can see here in right moment, I can actually rotate this platform all by itself and then just finish the rest of the print by itself. We have this small virus that generated during the motion process, but that can be trimmed, and this is sort of the final printing result and design result of this teapot. All right, now we have seen this working demo. Before we get into the detail of how we actually make it work, let's zoom out a little bit, talk about some of the related work, all right? So since the concept of interactive fabrication has been proposed, researchers have looked into different ways of trying to retighten this design and fabrication end. And roughly speaking, we can categorize that into 3 different categories based on the interaction mechanism. For example, the first category is what we call is turn-taking mechanism. Basically, the designer execute one command first, and then the robot and the machine actually do that in a physical way. Here's like one example. You can see here, the designer is doing something, and then the machine is doing something else after the designer is doing that. Although design and fabrication happened on the same object, they're not always happening at the same time because the designer and the machine have to alternate. A different approach to doing that is a hands-on design approach. Here you can see that the designer create everything all physically, and the 3D digital generated based on that from the computer. One problem with this approach is like that require the designer to physically deposit the material all by themselves. It's kind of like tedious and time-consuming. Finally, we have this in parallel printing mechanism, as you can see here. The designer can design the things into using a 2D screen using CAD modeling tools, and we have this printer to print this design at the same time. Now, in this on-the-fly print, design and fabrication happen at the same time, but they're not happening in the same place. Design is on the 2D screen, and printing is separated. So we have seen that for different categories here, it has its own pros and cons, right? For turn-taking, design and fabrication is not at the same time, and with in parallel printing, they're not in the same place. And with hands-on, this is also like require a lot of like manual effort. What we want to do with our RoMA system is trying to have like one step further from this. It's trying to allow people to design and print all at the same time without themselves to build everything with their hand. So the key to actually achieve this is trying to consider the design and fabrication in a larger scale. Imagine that the designer is not designed on a 2D screen, but actually step into a gigantic 3D printer to design and print inside a 3D printer. And by doing that, we can achieve a lot of things that only RoMA can do, but previous system is kind of hard to achieve. For example, by allowing people and the robotic arm to work in the same place, we can use the user's body as a design reference or other physical model, just bring it to the design scene as a design reference. In this simple example, we can use this hand to map the height of this teapot body. And also, by allowing designer and the robotic arm work at the same time, we can actually use partially printed part to support the next design steps. Here, the designer used the just printed part of the teapot body as a reference. The designer can actually put the finger against this physical model and design around his finger. And this is something we cannot do in a pure AR system, because in a pure AR system, nothing is actually printed. So it's hard for the designer to figure out like where to actually put the finger. But by combining design and printing at the same time, this is something we can do. And I think it's one of the very unique part with our RoMA system. And here's a similar idea. The designer is trying to create like a 2-floor Lego house. And the way to do that is like by printing the first layer first. And then the designer can put this Lego figure on top of the first layer and then use that as a reference to design the second layer. Now, finally, by combining design and fabrication together, we can sort of combining scanning, designing, fabrication into the one pipeline, and we can allow people to design and physically print directly onto an existing object. Let me show you one example of how the designer is going to create this feather jet stand on top of this existing model. All right, you can see the designer just put this physical model into our design scene, and we can use this controller to scratch on top of or on the back of this physical model. And basically what we're doing here is trying to copy this physical model surface into a digital format. And using that as starting point, the designer can design the 3D digital model directly onto this physical model, and then just handing this to the robotic arm. And with a careful calibration, we can directly print on top of this physical model. And you will notice that this design, scanning, printing, all this pipeline just all together waved into one uniform process, and all take just about 2 minutes from the beginning to the end of the printing. And that gives the designer a quick way to validate their design with physical prints. You can see we finished the printing. This designer can just take it out of the printer and see if it can balance itself and can stand. And I guess in this case it works, which is pretty good. But even if it's not working, the designer can simply just remove this part and do a next design iteration. So now we have seen all this benefit of the RoMA system, and let's look into how we actually make that work. And I will hand this to Jimmy, and Jimmy will explain how it works.
A system like RoMA can present a lot of complexity for a user, and that could be too much to handle if we didn't help the user out. We implement a proxemics-based interaction to help the user manage the complexity of the system. Proxemics was coined by Hall in 1966, and it discusses the way that spatial relationships between people and devices affect how different actors interact. In the HCI community, proxemics has been used to inspire large and small displays that adapt to how close users stand to them and how the users orient themselves with respect to the devices, as well as how the devices orient themselves with respect to each other and to users. The focus of our proxemic mechanism is the shared rotating platform that both the designer and the robot work on. Everything to the left of the center line of the rotating platform we call designer space. Everything to the right we call robot space. In general, the further the designer is from the robot space, the more control the robot has of the print. We further divide the designer zone into 3 subzones. Designer zone 1 describes the configuration where the designer is touching the rotating platform, as if to turn it or otherwise interact with it. Designer zone 2 occurs when the user is close to the platform but does not directly touch it. This happens when the user designs an object but doesn't rest their hand on the surface of the platform. Designer zone 3 occurs when the designer is far from the platform. Roughly, in proxemics discourse, these 3 zones are called the intimate, personal, and social zones. Depending on which zone the user is in, the robotic arm will either print or park. Let's take a look at how that works. In this example, the designer wants to rotate the platform, so he moves his hand onto the platform, entering designer zone 1. The printer, detecting that the user has entered its intimate space, retreats and parks far away. Let's watch. Notice that the printer interrupts what it's doing to retreat. The edge that it was about to print will be later rescheduled whenever it becomes available again for printing. In the next case, the designer is in designer zone 2, the personal space, but retreats away from the robot into designer zone 3. Now, the robot takes full control of the platform and finishes the print. Let's take a look. Notice that previously inaccessible edges close to the designer can now be printed immediately by the robot. There is a lot of engineering that went into RoMA, so we'll give you a quick overview of the hardware and software. Here is all of the hardware involved in our system. The most obvious thing might be the augmented reality headset, which is composed of an Oculus Rift and a OVR stereo camera attached to the front of it. The stereo camera's input is rendered directly to the Oculus, and then a virtual reality overlay is rendered on top of that. Next up is the augmented reality controller. This is an Oculus Touch controller that the user can use to interact with the virtual scene. We've also included a physical tip that allows the user to create correspondences between physical and virtual objects, and therefore interact with both the virtual and the physical scenes seamlessly. The other touch controller is outfitted with a pair of diagonal cutters, which is used for subtractive design. Next up is the robotic arm, which is equipped with a trio of force sensors so that it doesn't crush the print or the user. And it extrudes plastic, which is immediately solidified by multi-channel air cooling. Finally, the rotating platform is equipped with a touch sensor so that whenever the user needs to rotate the platform, the system is notified. And it employs a stepper motor and rotary encoder to handle automatic actuated rotation when the robot needs to print on the platform and the user is far away, as well as aligning the virtual and physical models. You'll notice that there are a lot of systems here, and they all need to be calibrated with respect to each other. I think there are approximately 6 different coordinate systems that we keep track of and keep closely calibrated. I won't go into it here, but it's a great section in the paper. The software pipeline is split roughly into 3 parts. The AR rendering module allows the user to create shapes in 3D space or with respect to already designed objects or design planes. As soon as the user is satisfied with what they create, they confirm it to print. It is then sent to the Rhino plugin, Rhino being a CAD program that we use as the central component. Once in the CAD system, the model can be saved and altered by a third-party system, or, more importantly, it can be turned into a wireframe, which is then sent to the printing module. In the printing module, the wireframe is scheduled dynamically, so that depending on which edges are available and which space the user is in, the printer knows where to safely print. Before we conclude, I'll speak briefly about the limitations of our work and some suggestions for future directions of work. RoMA currently produces good low-fidelity models, but flyaway strands can be unattractive and annoying. They also require manual trimming, well, if you want it to look nice anyway. We would like to produce higher quality prints to further optimize the design feedback loop and give designers a very quick idea of what their design will look like when it's finally done. We've also put a lot of work into balancing expressiveness and safety. RoMA currently uses an industrial strength robotic arm. This means we can get extremely precise prints, which is great, but it also means we have to be very careful with which interactions we allow the robot and the user to use. We can't allow a situation where the robot could accidentally harm the user. We are currently outfitting a human-safe robot with the rest of RoMA's hardware. This way we can try other interaction paradigms where, for instance, the designer and the robot are equal partners in design. The robot can access more of the designer's space, or even the designer follows the robot by augmenting a design rather than being the primary designer. We'd also like to consider RoMA as part of a full design pipeline. Before we go, we'd like to thank our collaborators, Cheng-Yao Wang, Kevin Go, Joseph Keider, Stefanie Mueller, Patrick Baudisch, and our advisor, François Guimbretière. And that's about all. Thanks very much for your attention, and we'll take questions.
We're a little over time, so we have time for one quick question.
Hi, Tiffany Wan from the University of Calgary. I was wondering if you were thinking about, does your system take structural integrity into account? Because historically, we've known with like freeform 3D printers, if things shift, then it's very easy for a print to fall apart. So how does your system take that into account if it does?
So I just want to repeat your question, make sure that I fully understand. So you're saying it's like if the print is cannot say stand on itself or it's false, how will you take care of that? Is that?
Yeah, so basically if you had a model that wasn't very structurally sound and then like halfway when it was printing, it just kind of fell over or shifted.
Right, it's a great question. So for most of the things we have tried and printed because we have this air cooling and wireframe structure, for most of our test cases that doesn't happen. But in our future work, we're thinking to combining that with sort of the structural analysis in our software computational component that can support that.
Okay, great, thank you.
Thanks.
All right, on that note, I would like to thank the speakers again. And also all the other speakers in the session. And that concludes our session. Thank you all for being here, and I hope to see you all at WIS 2018 in Berlin. And have a great lunch.